Auzu billahi minash shaitanir rajim. Bismillahir rahmanir rahim. Dear student, assalamu alaikum. Today the topic of our discussion is fluorescence and its instrumentation. You know that we have discussed what is fluorescence and different types of fluorescence. Today is the 30th lecture of a course molecular spectroscopy having chem code 451. I'm Dr. Muslim Khan, Assistant Professor, Department of Chemistry, KUST. First of all, what is fluorescence? As we have discussed, this is the type of photoluminescence in which the radiations are emitted during the de-excitation process of an electron from singlet to singlet ground state. We have discussed the singlet state and singlet ground state and also a triplet state, and also we have discussed the Jablonski diagram for fluorescence, phosphorescence, internal conversion, de-excitation process. All these things we have discussed and detailed in our previous lecture. So today we will be more focusing on the instrumentation of fluorescence or fluorometer. So when going towards the fluorometer, all the type of fluorometers having the following basic components. First of all, this light source. This light source is necessary in fluorescence for the excitation of the sample. And then wavelength selector, which we select the wavelength for the sample, and then sample cells. And then like when this sample is get excited, so then it is coming towards the ground state. It must emit some energy, so emission will be occur. So excitation wave, we need excitation wavelength, and then excitation intensity, and then we need emission wavelength, and then filters we need, so then which can filter uh, the the desired wavelength of the radiation. So but there is a difference in the angle of arrangement of these components. There are basically three types of arrangement with 45, 90, and 180 uh, and zero angles. But the most common is the 90 angle arrangement to avoid interference of the transmitted radiations. Space requirement are also not much great. Uh, the means, as I told you, the detail about this instrument. So, so this is the basic layout of the fluorometer. That basically these are the components which are there in a fluorometer. First of all, light source, as I mentioned it in my previous slide, and then monochromator, because polychromatic light is coming from this light source. We need a light of a single wavelength to excite the sample. So this monochromator is to eliminate all the other unwanted uh, light of a wavelength, and then the sample is it get excited, and then there will be emission from the sample, because that is going to the excited state. When coming back to the ground state, there another monochromator is needed, which is which is called a fluorescence monochromator. So it means that in fluorometer there are basically two monochromator are used. One is to isolate all the unwanted light coming from the light source. So this is excitation monochromator, and this is a fluorescence monochromator, emission monochromator. And sample cells, which we keep the sample there, and sample is get excited, and then this emitted light coming from the this one, this also then uh, remove all the other unwanted light which is coming from the sample, the emitted light, and then it's going to the detector. Different kinds of detectors are used. Filters are used, slits and polarizers. So we will discuss these in our coming slides. So while discussing the fluorometer, we will discuss the three type of design. Three type of designs mean simple and then medium and then going to the hard one. So this is a simple diagram of a fluorometer. As I told you, like xenon lamp is used as a source of light. There are different types of light sources are used. We will discuss in our in our coming slides. And then when this light is coming from this polychromatic xenon lamp, that is striking to the mirrors and then to the grating. So this is basically a monochromator. This is a excitation monochromator. We have discussed the monochromator in our previous lecture, that what is monochromator. Then we get rid of the unwanted light, and then this monochromatic light is going to the sample, where it is the sample is get excited by this monochromatic light, and then this light is going to the emission monochromator, again having same grating and lenses, mirrors, and then this light is going to the photo multiplier tube, PMT, photo multiplier tube, which is a detector and fluorometer, and get detector, and we get a spectra for fluorescence. This is a simple. So two light sources are used. Um, and one for excitation and one for emission. Two monochromators I use, one for excitation and one for emissions. So this is a medium diagram, means diagram is getting more, little bit more, giving you the actual version. So light source, and then these things we will I will tell you in a more hard diagram that what are these things. This is a little bit more complicated diagram in comparison to the first one. And then this is excitation monochromator, and then these lenses and sample, and then this is emission monochromator, and then photomultiplier tube detector. This one is giving you the more detailed view, the hard mode of a fluorometer. First of all, look at this light source, xenon arc lamp. Light is going from light source to the first excitation monochromator. In excitation monochromator, we use grating, so which disperse the light to the mirror, and then this mirror to this mirror, and then from this dual grating excitation monochromator, light is going to the sample cells. First of all, here is a shutter, and then from shutter there is a filter holder. You can see it. This is a this is a filter holder, and then beam splitter, which split the beam. The half of the beam is going to the reference cell, where we are keeping our reference solution, and half is going to the sample holder. And then this there is a polarizer, uh, and then this light is going to the optical module, and this is going to the emission monochromator. So here again grating and lenses, and this is fixing this emitting light into the PMT photo multiplier tube. So this is the more hard and more detailed view of fluorometers and instrumentation. So while measuring emission spectra, the procedure is like we have discussed this this fluorometer. First of all, white light source, this xenon lamp, make it on. Shift excitation grating to a desired wavelength. You know somehow that what is the lambda max of your sample. So shift excitation grating to the desired wavelength, and light enter the sample chamber. Then light hit the sample, then, and emission from the sample enter emission monochromator. Set emission grating on your desired wavelength, and then this emission light is detected at photomultiplier tube. So then we are getting this is EM raster emission grating. EM grating is used in this emission monochromator. So this is we are basically in getting two spectra, and one is this absorption spectra, and one is this emission spectra, excitation at 450 nanometer. This is photo 450 nanometer. Uh, uh, the procedure is I told you that first of all make a white light on and shift excitation grading to the desired wavelength, and light enters into a sample chamber, hit the sample, and then light is coming to the emission monochromator, and set emission grating, detect emitted light at photomultiplier tube. So uh, while discussing the excitation spectra, first of all, your sample is absorbing the light. It is going from the singlet state, ground state, to a singlet excited state to the S1. These are the different vibrational levels in S1, excited S2, and S3, V1, V2, and V3. So this is where it is getting a absorption occur, and the sample is absorbed. And when it is directly coming from here to here, this is called a fluorescence. This is S2. When it is going from S, it is going to S2 rather than this one. This is from S0 to S2. It is excited to this internal conversion, as we have discussed in Jablonski diagram. So this is the third one. This is excitation spectrum when it's going to the S3. Uh, these so these are the this is the excited fluorescent emission spectrum is the same regarding of the excitation wavelength. This is, you can see the mirror image of absorption spectrum going to here and here. This is IC internal conversion, but intensity changes in this emission spectrum. This is this monitor in a scan through excitation wavelength, and this monitor, this emission spectrum monitor emission fixed wavelength of whatever it may be. This is a wavelength maybe 400, 500 nanometer, etc. Different wavelength. So measuring excitation spectra, the excitation spectra, this the procedure is somehow similar to the emission spectrum. Shift this emission grating when you are measuring excitation spectra, grating to the desired wavelength, and shift excitation grating to stating wavelength. Light source on, then light hit the sample coming from here. Emission from the sample enter into emission monochromator. Detect emitted light at photomultiplier tube. This is the procedure. And this is the excitation spectrum, and this is the absorption spectrum. So if emitting from a single species, excitation spectrum should match absorption spectrum. So, coming to the more detailed discussion of the fluorometer, there are different sources of light. First of all, this mercury arc lamp. Mm, in a molecular spectroscopy, different types of light sources are used: mercury arc lamp, xenon arc lamp, and uh, tungsten lamp, and the last one is this tunable dye laser. In a molecular spectroscopy, different light sources are used, like xenon lamp is used. This xenon lamp is used in the UV visible region. Tungsten and tungsten halogens lamp are used in the visible region. Similarly, this mercury lamp, The first one is used in the emission from the xenon, and occurs in like in the range of 250 to 800 nanometer. The other lines are 365, 394, 3, etc. Depends on the specific wavelength of the sample. Different sources are used. And like first of all, this mercury arc lamp, this is producing intense line spectrum above 350 nanometer. This is a very high pressure lamp, gave lines at 366, 405, 436, 546, 577, 699, and 734 nanometer. Uh, Low pressure lamps even give additional radiation at 254 nanometer. This is an example of a mercury arc lamp. The second one is a xenon arc lamp. Intense radiation by passage of current through an atmosphere of xenon. This is the example of xenon arc lamp. The spectrum of xenon arc lamp is a continuous spectrum and over the range from 250 to 600 nanometer. The peak intensity is about 470 nanometer. This picture is taken from Encyclopedia Google. Uh, so the next one is a tungsten lamp. The intensity of this lamp is low. If the excitation is done in the visible region, then this tungsten lamp is basically used, and it does not offer UV radiation. So you can't use this tungsten lamp when excitation is needed in the UV region. This one is a tunable dye laser. This is the fourth light source used in the fluorometer. The pulsed nitrogen laser is the primary source in this tunable dye laser, a light source used. The radiation range of this tunable dye laser is between 360 to 650 nanometer, which is produced in this. These are the different light sources used in the fluorometer. And the next one is the next thing is very, very important: filter and monochromator. So primary filter absorb visible light and transmit UV light, while secondary filter absorb UV radiation and transmit visible radiation. So there are two types of wavelength selector used in this case. One is this excitation wavelength. These select the radiation of a specific wavelength for the excitation at which excitation occur. So excitation monochromator isolate only the radiation which is absorbed by the molecule, while emission monochromator isolate only the radiation emitted by the molecule there. The de-excitation wavelength selector, these select the wavelength of the radiation that are emitted during de-excitation process. The wavelength selector may be monochromator or filter. If the spectro, if the spectro is used, the monochromator is used, while in fluorometer, the filter are used. If the wavelength are known, then filter fluorometers are best. But for the development of a new method and wavelength estimation, spectrophlorometers are used, and this is called scanning phenomena. This is a very important scanning phenomena. So a filter and monochromator both are used, depends which type of instrument basically you are using. This is very important sample cell. Rectangular shaped cells are used in order to reproduce the result or to be placed in the same position. These are made of quartz usually. The majority of fluorescence assay are carried out in a solution. Cylindrical or rectangular cells fabricated of silica or glass tubes or quartz used in the path length is usually between 10 millimeter or 1 centimeter. All the surface of the sample holder are polished in fluorometry basically. Uh, The last thing is the detector. Different types of detector are used: photovoltaic cells, phototubes, photomultiplier tubes. Best and accurate are the photomultiplier tubes. Here you can see the photomultiplier use. Multiplication of photons electron by secondary emission of radiations. This is how, this is basically a multiplication of photon. Here you can see the multiplication. A photocathode and series of diodes, these are diodes, are used in this case. We have discussed also this one before as well. Each cathode is maintained 75 to 100 volt higher than the preceding one. Overall amplification of 10 raised to the power 6, which when it is reaching here, is obtained in this case. So these are different these are different detectors. Um, Different types of two, like single beam fluorometers and double beam. Tungsten lamp is a source of light. The primary filter absorb visible radiation and transmit UV radiation. Emitted radiation measure at 90 angle by secondary filter. Secondary filter absorb UV radiation and transmit visible radiation. Advantages: this is simple in construction, easy to use, and economical. While it is not possible to use reference solution and sample solution at a time because this is a single beam. Rapid scanning to obtain excitation and emission spectrum of the compound is not possible. The double beam instrument, similar to single beam instrument, but two incident beams where light is split into two. Half of the light is going to the reference cell and half is going to the your sample cell. The emitted radiation from sample or reference pass separately through secondary filter. Advantages, this is means you can use this reference cell here. So factor affecting, these are the factor which affect fluorescence. We will discuss these in detail in our coming lecture. So these are the books you can use for this one. G.T. Christian, Instrumental Analysis, Scooch, Douglas and Scooch, Principle of Instrumental Analysis, and B. Wells Sperling, Atomic Absorption Spectroscopy. Thank you very much.